Hello everyone. The topic of this talk is integrated sensing and communication with mmWave Massive MIMO, a compressed, sampling perspective, based on a recent paper from Dr. Z.Gao's group in the Beijing Institute of Technology. This talk contains 4 parts as shown in the slide. The first part is introduction. Since 2020, 5G has been widely deployed around the world. It provides enhanced communication service, while also resulting in high energy consumption and carbon emissions. So, an important problem in the research beyond 5 and 6G is how to realize powerful but green wireless systems. Integrated sensing and communication is regarded as a promising paradigm shift in both 5G and 6G. Integrated sensing and communication combines the functions of communications and radar by sharing the spectrum, hardware, or waveform, which is able to save cost and reduce carbon emissions. More importantly, it can support many emerging applications and scenarios in future wireless systems, such as extended reality, self-driving, LEO communications, smart cities, and so on. Generally, integrated sensing and communication is classified into 2 types. The first type is radar communication coexistence. In such type, the communication and radar use independent hardware components and share only the spectrum resources. Therefore, interference suppression is necessary at the receiver. The other type is dual-function radar communication. That is DFRC, which combines radar and communications more firmly. There will be a DFRC station responsible for both communication and radar tasks, sharing the spectrum, hardware, waveform, and so on. The interference suppression is no longer necessary, but the enhancement to the receive signal processing may be required. In our work, we will focus on DFRC. Particularly, we consider the Massive MIMO for integrated sensing and communication. In fact, Massive MIMO is naturally an intersection between modern communications and radar. On the one hand, Massive MIMO is the main enabling technology in 5G, providing high spectral efficiency for multi-user communications. On the other hand, Massive MIMO can be regarded as an enhancement of MIMO radar. The large spatial aperture of Massive MIMO is able to realize high-precision sensing, or say, imaging, as shown in this slide. So this motivates us to ask, how will Massive MIMO reshape integrated sensing and communication in the future? And we try to find a solution in this work. A challenge for the application of Massive MIMO is that a massive number of antennas introduce a significant computational burden and signal overhead in both communications and radar sensing. Therefore, compressive sensing, which can recover signals from reduced measurements by leveraging the intrinsic sparsity, will be a promising solution for integrated sensing and communication. We will not go into the detail of the introduction of compressive sensing, and the audiences can refer to the literature review in our paper. Then we will talk about the system model considered in this work. First, we propose an DFRC transceiver architecture based on mmWave Massive MIMO, as shown in the slide. The proposed architecture consists of 1 communication unit, that is, CU, and 1 radar unit, that is, RU. A critically spaced array, that is, CSA, is adopted at the CU and it is responsible for the communication task, while a widely spaced array, that is, WSA, is designed for the RU to receive the radar echo signals. Note that the element spacing in CSA is half wavelength, while that in WSA is larger. We guarantee that the physical aperture of WSA is larger than that of CSA. One of the advantages of the proposed DFRC architecture is its energy efficiency due to the following properties. First, we consider hybrid beamforming architecture for the CU, which reduces the number of required RF chains. Second, the RU only receives the echo signals for radar sensing with the received RF chains, as shown in the slide. The receive RF chain does not have an energy-hungry power amplifier, and the low-resolution ADC in the RU further reduces the energy consumption. Besides, we can see that this architecture does not need to modify the hardware in current communication equipment. That is to say, we can directly deploy the RU beside the current base station to realize the transition from conventional communications to advanced integrated sensing and communication. This also avoids the use of difficult and immature full duplex techniques, since the different units are responsible for transmitting and receiving, respectively. The other advantage of the proposed architecture is its high spatial resolution. Compared to CSA, WSA can realize a larger spatial aperture with fewer elements, and thus has higher spatial resolution, but with ambiguity, as shown in the slide. If the element spacing is larger than half wavelength, there will be mirroring beams for certain directions, which may introduce interference in communications and blur the angle estimation in radar sensing. This phenomenon is also called spatial aliasing. However, we can eliminate this ambiguity by jointly exploiting the information from CU and RU, which will be discussed later. Also note that the current commercial radar modules also deploy WSA, but only at the transmitter side. We improve such architecture by removing the WSA to the receiver side, which avoids the influence of ambiguity on communications. Then we focus on the channel model of the systems. We consider the time-varying channel model and formulate the channel as the sum contribution of a few clusters, and each cluster contains a few paths. The radar channel contains the information of range, direction, and speed of the targets of interest. Note that a key issue is that we assume the arrays of CU and RU are collocated and are parallel to each other so that they see the targets at the same directions, which is called spatial consistency. This is a widely adopted assumption in classical literature on radar processing. For the communications, we consider the Rishon fading channel model with one line-of-sight path and a few clustered non-line-of-sight paths, as shown in equations 1 to 5. On the other hand, the channel for radar sensing from the CU to the target and then back to the RU can be formed as equations 7 to 10. Note that the aforementioned spatial consistency results in the same AOD at the CU and AOA at the RU for each target. As shown in equations 8, it is a key property to eliminate the ambiguity brought by the WSA, which will be discussed. Then we will talk about the proposed pilot waveform design. Although the channel models are time-varying, some or all of their parameters may be reasonably assumed to be time-invariant under different timescales. On this basis, we propose a transmission frame structure for integrated sensing and communication, as shown in Figure 2. 3 timescales are considered. The small timescale, which is much shorter than the channel coherence time, makes the whole channel can be assumed to be time-invariant, and we use the pilot in such timescale to estimate the initial channel values. In a moderate timescale, and the positions of scatters or targets are relatively stable, yet the channel coefficients may vary significantly due to the Doppler effect, so it would be used to accumulate the Doppler effect and to estimate it. In a large timescale, the environment may experience dramatic changes. A mission and radar sensing stage should be carried out to capture the changes. First, we focus on the small timescale, where the channels are regarded as time-invariant, and we use the time domain training sequence of length p as a holistic waveform for both communications and radar sensing. Note that the length p should be much smaller than the channel coherence time. Find the channel impulse response, CIR, in the spatial delay domain. As shown in the matrix HSD, note that the radar CIR in the spatial delay domain contains useful information. For example, initial positions and shapes. of the targets, so we focus it accurately at the current stage. Further data processing for extracting the features of the targets can be left as future work. By using the linear convolution expression, we can obtain the observations of the communications channel and radar targets in equations 13 and 14 respectively. Furthermore, the observations are aggregated as the matrix form in equations 15 and 17. Of that, the communication channel observation is a widely considered channel estimation model for massive MIMO, and it can be solved by off-the-shelf compressive sensing methods. However, the CIO in equation 15 contains the properties of ambiguity brought by the WSA and spatial consistency, and these properties cannot be fully utilized by the traditional compressive sensing algorithm. So it is necessary to design a new compressive sensing-based algorithm to estimate the radar CIR in equation. We will consider the waveform design under hybrid beamforming architecture, where the switch of the phase shifter will take non-negligible reconfiguring time. However, this property is often ignored in existing literature. Given that, we propose to use a codebook of analog precoders and efficient idle time for reconfiguring phase shifter between two adjacent code words, with the loss of pilot diversity. Taking the analog precoders as an example, the codebook is designed as the blue part. Note that the number of code words is much less than the number of pilot signals. According to compressive sensing theory, this degraded pilot diversity will affect the performance of sparse recovery. Therefore, the number of code words should be chosen appropriately.
This figure shows the proposed waveform design, which realizes the trade-off between the pilot diversity and codebook size. The key is that during the stage of uncertain analog precoders, zero baseband signals are transmitted, that is, the actual transmitted signals are also zeros. In other words, the guard interval between two different analog precoders and thus avoids the influence of uncertain analog precoders. Note that the all-zero guard interval does not mean that there is no pilot signal received at the receiver, since the tail part of the previous pilot signals can be received by the receivers, contributing to the effective measurements for channel estimation. Meanwhile, at the receiver, the signals associated with the uncertain analog combiners should be removed from the valid measurements, reducing the dimension of measurements for communication channel estimation. Then we will talk about the proposed CS-based scheme.
To resort to compressive sensing, we should transform the spatial delay domain CIR into the angular delay domain CIR and utilize its sparsity. So we should design the dictionary, especially for the WSA, to realize the transformation. For simplicity, we single path associated with the WSA. A direct method for estimating the angle is to find the peak of the correlation function between the actual steering vector and a probing vector, as shown in this slide. After mathematical calculation, we can see that the correlation function is by the absolute Dirichlet kernel function.
We plot the correlation function along the horizontal direction in Figure 4, based on which we can summarize two essential properties of the WSA. First, we see that with the element spacing larger than the half wavelength, the correlation function will exhibit periodicity, and thus the WSA suffers from angular ambiguity. Peaks exist for a single path, and it is hard to determine which peak corresponds to the actual channel direction. On the other hand, the WSA has a higher angular resolution in its non-ambiguity area, that is to say, the beam width in one of the periods will be narrower than that of CSA, since the WSA spatial aperture even with fewer elements. This motivates us to eliminate the ambiguity of the WSA so as to embrace its high resolution. Based on the analysis above, we choose only one of the non-ambiguity areas of the correlation function and quantize it based on uniform angular sampling, and then re-represent the radar channel accordingly. The angular domain channel obtained after the transformation will exhibit angular sparsity in the mmWave band, which can be exploited by. However, this procedure is quite similar to the conventional formulation of sparse MIMO channel estimation, so what is the difference? The key is that we choose only the non-ambiguity area to quantize. This can guarantee that there will be only one peak for each effective target in the angular domain channel, however corresponding to this peak is not necessarily the actual angle of the target. To show this point, we compare the proposed dictionary design to the traditional dictionary design for the CSA in this slide, where the element spacing of the WSA is one wavelength and 2-point targets are considered. We can see that the dictionary for the WSA only covers a smaller angular range to guarantee only one peak angle component in the angular domain, compared to the CSA. The angular domain channel is likely to be sparser by using the WSA to suppress the power leakage caused by the off-grid angles. However, the peak in the angular domain channel associated with the WSA may correspond to a false angle. Simply treat the peak as the position of the actual angle. It may make the DFRC station estimate the wrong target, causing harmful misdetection or false alarm. Still, we should solve this ambiguity. Fortunately, due to the spatial consistency, the elimination of ambiguity is possible. In our work, we propose an orthogonal matching pursuit, OMP, algorithm with support refinement, which is an improved version of the original OMP algorithm, to solve the radar sensing problem. The main difference between the proposed R and the traditional OMP is twofold. First, we note that the AOD at the CU and the AOA at the RU basically stand for the same angle due to spatial consistency, and the AOD estimate at the CU with CSA has no ambiguity. So after we obtain the estimates of these two angles, we can refine adding the integral number of periods so that it approaches the AOD estimate. In this way, the ambiguity can be eliminated. Then, as discussed before, the AOA estimate will be more accurate due to the high resolution of WSA, so in each iteration of the proposed OMPSR, we will replace the AOD estimate with it and refine the sensing matrix. This refinement will help the sensing matrix to better model the angular domain channel of the radar, and thus improve the radar sensing performance. For the channel estimation for communications, since the analog architecture is deployed, the dimension of the received pilot signals in each time slot is limited to 1 at the user, which makes it hard to recover the whole communication CIR. Moreover, the energy-constrained user has limited computational capability compared to C station. Given the above two limitations, it is practical for the user to estimate only the line-of-sight angles and delay via the formulated problem. The procedure of the channel estimation is summarized in Algorithm 2, which is a single correlation step of the OMP framework, and it returns the position of the most significant atom line-of-sight path component of channels. This single-step solution has low computational complexity and makes it practical for implementation at energy-constrained. Then we will talk about the Doppler estimation. The Doppler estimation and compensation are essential for integrated sensing and communication. We focus on the Doppler estimation for uplink line-of-sight communication, and the proposed method can be directly applied to the speed estimation of radar targets. With the estimates obtained at the previous stage, the DFRC station to user scheduling, that is, choose some users which are well separated in either the angular domain or the delay domain to serve simultaneously, in order to avoid severe inter-user interference. The number of users should not be larger than that of RF chains at the DFR. After scheduling, each user transmits pilot signals are depicted in Figure 6. To be specific, each user emits an uplink impulse pilot signal, which is marked by the green pulse in Figure 6, between every two data frames. The zero padding is also added on both sides of the impulse pilot signal to eliminate interference. With this arrangement, we can write the received pilot signals for each user as equation 40. As we argued before, with the user scheduling, different angles and delays of different users will significantly suppress the inter-user interference, and thus we can safely treat the inter-user interference. As a result, during the Doppler estimation procedure, the time observation can be viewed as the noisy uniformly spaced samples of a single-tone complex sinusoid, whose frequency is the interested Doppler frequency for each user. Many off-the-shelf techniques can be used for estimating the Doppler frequency, while we will use the autocorrelation linear predictor algorithm for its near-optimal performance. Then we will move to simulation results part. Please refer to our paper for the detailed simulation parameters setting. First, we investigate the convergence of the proposed OMPSR algorithm under different channel conditions. It can be seen in Figure 7 that algorithm 1 converges reasonably fast and it achieves good NMSE performance under different channel conditions. Figure 7 also provides insight into choosing criterion for the OMPSR algorithm. Unless stated otherwise, we will choose the number of iterations in algorithm 1 as 100. Figure 8 reports the NMSE performance as the function of the inter-element spacing of the WSA under different dictionary dimensions. Observe that within certain regimes, increasing inter-element spacing in dictionary dimension significantly improves the NMSE performance of radar sensing, since they result in finer angular reservoir analysis. By contrast, the NMSE performance exhibits no improvement with increasing inter-element spacing beyond the certain regime. Note that increasing dictionary dimension enlarges the dimension of the compressive sensing problem while increasing inter-element spacing would lead to a bulky antenna array. Therefore, these parameters should be carefully chosen to strike a balance between system performance and hardware complexity. To investigate the proposed pilot waveform design, we plot the NMSE performance as the function of the codebook size in Figure 9. We also depict the idealized case where the analog precoders could change in each sample without reconfigurable time, which forms the lower bound of the NMSE. As radar sensing suffers from the limited pilot diversity when the codebook size is small, while the sensing performance improves with codebook size quickly, reaching the NMSE performance very close to the idealized lower bound. In practice, we can choose some appropriate codebook sizes for not only achieving good sensing performance, alleviating the storage burden at the DFRC station. Figure 10 compares the performance of the proposed OMPSR algorithm with two existing schemes, the original OMP algorithm without the support refinement, and the block OMP algorithm which only utilizes the delay domain sparsity. It can be seen that the OMPSR outperforms the other two schemes significantly of downlink transmit power and for different quantization bits, as it takes full advantage of the higher angular resolution of the WSA and the spatial consistency. To intuitively show the performance of radar sensing, we compare the estimated results to the true values of the angle and range parameters for a single-channel realization in Figure 11. It can be seen from Figure 11 that by using our OMPSR algorithm, all the target's angles and ranges can be accurately estimated. By contrast, if we only use the angle estimates without support refinement, although the delay estimation is as accurate as that obtained by the OMPSR algorithm, the angle estimation exhibits severe blurring due to the angular ambiguity induced by the WSA. Therefore, the proposed support refinement necessary when WSA is considered. Next, we investigate the communication performance under the proposed integrated sensing and communication framework. We adopt the average spectral efficiency to evaluate the performance of line-of-sight component estimation in the low-complexity algorithm 2. Figure 12 depicts the ASE performance, line-of-sight angles, as a function of the downlink transmit power, against various values of dictionary dimension. It can be seen that compared with the non-redundant dictionary, the redundant dictionary design significantly improves the ASE performance given the same pilot overhead. Furthermore, Figure 13 ASE performance as the function of user codebook size. Similar to Figure 9, Figure 13 shows that fewer available analog combiners lead to poor ASE performances while increasing codebook size significantly improves the ASE performances. The results of Figures 9 and 13 waveform design is effective and necessary for hybrid beamforming-aided integrated sensing and communication systems to realize pilot diversity under practical hardware constraints. We further investigate the effectiveness of the proposed Doppler estimation scheme. Figure 14 compares the average MSE performance of Doppler estimation with or without inter-user interference. We also plot the Kramer-Rao bound, CRB, of the singletone frequency estimation problem. We've seen that when the number of observations is smaller, the influence of inter-user interference is not serious and it hardly affects the Doppler estimation, hence, the MSE performance with inter-user interference can attain the CRB without inter-user interference, particularly in the low transmit power regime. for a larger number of observations, the MSE performance deviates from the CRB as transmit power increases, leading to an error floor. This is because in such cases the inter-user interference dominates, however. This MSE gap only makes a negligible influence on the real communication performance, as seen. Figure 15 plots the downlink bit error rate, BER, performance with or without Doppler compensation. The estimated Doppler frequency obtained by the proposed scheme is used to compensate for the Doppler effect of the line-of-sight path. It can be seen from Figure 15 that without Doppler, severe inter-carrier interference caused by the Doppler effect degrades the BER dramatically. While the BER with the estimated Doppler compensation is almost the same as that with the perfect Doppler compensation, even though the MSE performance cannot achieve the CRB. This means that the proposed scheme for Doppler estimation is vital for combating time-varying channels in communication-centric integrated sensing and communication systems. That's all. Thanks for your listening and questions are welcome. Thank you.